My name is Federico Malerba, and I will be presenting today this paper on evaluating tunable agents with nonlinear utility functions under expected scalarized returns. So for those of you who may be unfamiliar with the tunable agent setting, here's a brief explanation of it. In the traditional scenario, we have an agent who receives a state and outputs an action. But in reality, we actually have a function u that establishes what the optimal action for it should be, and we want the agent to output the optimal action for the given u. In the tunable agents framework, we want to be able to swap the utility function u with u prime, and then we want the same agent to understand the new utility function and give us the action that now optimizes for u prime. A general framework for this was proposed by Castro and Heinz and is shown in this figure. What we can see here is the classical scenario where we have an agent interacting with an environment. However, they're not only interacting via the actions and the state observation, but there is also a reward system that is between them. The reward system takes in input events and preferences and outputs a reward that is fed to the learning algorithm. It is important to note that in the context of our paper, we call reward only the multi-objective vector, and instead we refer to utility when talking about the scalar value that is the result of mapping the multi-objective vector via the utility function. Also, the term preferences is undesirable for the general utility functions. And so we instead refer to this as a utility function parameterization. It is important to note that in this work by Castro and Heinz, they only dealt with linear utilities, and that is why they use the term preferences, whilst our objective is to test nonlinear ones. The first question one may ask is why even go for a nonlinear utility functions? And there are three main reasons why. The first is that there are known Pareto-front limitations to linear utilities, namely that they're not able to reach policies that sit in the concave region of a Pareto front. Further, nonlinear utility functions may be more intuitive to real people. For example, a threshold activation where it might be easier to say, I want minor accidents to be less than 10, rather than saying I value minor accidents minus 0.5. And the third reason is also related to real users, and it's that real users may well have nonlinear utility functions. And if we are to develop algorithms to solve problems for real users, we need these algorithms to be able to optimize for such utilities. An important constant that is required is that of the cumulative reward vectors. Intuitively, this is just the sum of the reward vectors obtained over the episode. For nonlinear utility functions, it is necessary to keep track of the CRV because the utility that the agent has to gain from a reward vector depends on the previous rewards obtained. For a simple example, in the case of a threshold utility, it makes a difference whether the agent is above or below the threshold. Feeding the CRV to the agent has its drawbacks since, for example, not in all scenarios at runtime rewards may be available to the agent. In particular, there are many real-world settings in which one might imagine that rewards are only available at simulation during training and not available at implementation. An alternative to this would be to give the agent memory. So, for example, structure the agent as a recurrent neural network. But this would make the training more complicated. And so within the small context of our experiments, we did not do this. We just fed the agent with the CRV. The problem we considered was that of the gathering environment, which was also the subject of the paper I mentioned previously by Castro and Heinz. An image representation of it is given in this image. In the bottom left corner is our agent, whilst in the upper right corner is a deterministic agent that has a simple heuristic policy, and the deterministic agent is only interested in red items. The items are fixed in their numbers, that is, there are always 3 red items, there are always 3 green items, etc. But their location on the grid is random within the central 4x4 grid that you can see them in right now. All the agents that we trained in this work follow the architecture shown in this figure. We have three RGB images coming from three consecutive time steps fed to the agent, which are passed through two convolutional layers with 256 filters. The resulting features are then flattened and concatenated with the utility function parameterization, and optionally with the cumulative reward vector. I say optionally because we tested both providing and not the cumulative reward vector to the agent and compared the results between these two approaches. All the inputs are then passed through a fully connected neural network that outputs the scalar Q values for every action. And we trained 4 different agent models, all following this structure, but having a varying number of layers and nodes in the fully connected portion of the model. This was to test different complexities of a model and see how they affected performance. For the experiments conducted in this paper, we tested 4 different families of utility functions. As a baseline, we used linear utilities. These have already been present in a lot of our literature, and they were the main utility functions against which we compared. They are simply defined by taking the dot product of a weight vector with the multidimensional rewards. There are many scenarios where one might instead be interested in reaching at least a certain threshold for a given objective, because otherwise there might be no positive impact. So to model these scenarios, we introduced threshold utilities. These also have a weight vector, but the dot product is only taken for those entries in the reward vector that have passed their respective threshold. Analogously to threshold, we have dual threshold utilities. These work pretty much the same as threshold utilities, except that the dot product is only applied up until the threshold, and then the utility component for that objective remains constant. One can think of this as a hard version of the famous law of diminishing returns, which is that after reaching a certain target for an objective, there is no interest in getting any more of it. Finally, we use target utilities, which were first introduced in a very recent paper. The target here is the R dagger vector that you can see in the formula. Without getting too much in the details of how they work, it is sufficient to say that the agent is rewarded for going in the direction of the target vector. Note that if the agent is given a non-Pareto front vector, it will still maximize its utility by reaching a Pareto front vector in the direction of the target vector. It is important to point out that threshold and dual threshold utilities contain linear ones. In fact, if we take a threshold of 0 for all entries or a dual threshold of 31, we obtain functions that are mathematically equivalent to linear ones. The reason why I chose the number 31 is because there are at most 31 time steps in our environment. At most 30 time steps in our environment. So there's no reward entry that ever goes beyond 30. So 31 is a dual threshold that's valid. This is useful. It's useful to know that threshold and dual threshold utilities contain linear ones, because on the results shown later, we'll see agents that were trained on these utilities, on threshold and dual threshold utilities, but were evaluated afterwards on linear ones. The reverse, unfortunately, is not possible. So for evaluation, let's just say that it's quite problematic. And the reason is that one might first think of using average utilities to compare agents. But the problem is that when you're dealing with utility functions that are coming from different families, their utility values are not comparable. They're not comparable in magnitude. It's not comparable the fact that the agents are attempting to seek different objectives, and they might all do it in an optimal way, but get utility values that are drastically different because of what their objectives are. So this is just not an approach that is usable, unfortunately, when one is dealing with multiple sets of utility functions. Instead, what we decided to go for was considering end of episode reward vectors. So essentially the cumulative reward vector at the last time step. This comes with its own problem, and there are two main problems. One is optimality. We do not know which end of episode reward vectors are optimal. And this is just a feature of reinforcement learning. We do not know what is optimal. We just know what the agent has done, and we don't know where that is optimal or not. And the second thing is we don't know what's reachable. So, for example, in a chess game, imagine you had a chess game with a reward vector with an entry for a number of turns and an entry for taking every chess piece. The reward vector that corresponds to 2 turns passing and taking the queen and the rook is not reachable. It's impossible to take the queen and the rook in 2 turns in chess. And this is a simple example where it's easy to say, okay, yeah, this is not a reachable vector. But if I were to very slightly complicate this by saying, okay, is it possible at turn 10 in a chess game to take queen, rook, and 3 pawns? All of a sudden, you might realize how complicated this is. It's very difficult to determine a priori what is reachable and what isn't. And for complex environment, this becomes completely unfeasible. And so the way we deal with these 2 problems, well, for optimality, we drop it and we instead refer to dominance. So the concept of dominance is something you might already be familiar with. It's just the partial ordering on the on Rn. And for reachability, what we do is we use a common environment. So what we can now do is test agents on a common environment, see what are the dominating vector that they have. And we know, since the environment is common, we know that any vector that an agent managed to reach and that is dominating another agent, the other agent could have reached it. So we know that the dominance is a real dominance. It's not that the second agent couldn't have done that for whatever reason. It's just the second agent is worse than the first one. It could have done a better thing and it didn't. And this is a combination of using the dominance as a metric and measuring it on a common environment. In principle, the common environment could be many common environments. One could sample hundreds of common environments. It becomes computationally quite expensive to do this. But in our case, we only took one. So we have one fixed environment, which is precisely the one shown in figure here. The only interesting thing about this fixed environment is that we made sure that the agent has complete control over playing competitive or collaboratively with the other agent. So the other agent, as I mentioned, is interested in red items. Here, our agent has complete choice over whether taking all 3 red items or leaving all 3 to the other agent. And so this is not always the case, depending on how the items are randomly initialized, but in this fixed environment, it is. Agents were not trained specifically to behave in this environment. They were trained on random environments with random utilities, and then they were evaluated on this fixed environment. The agents trained, so we have a lot of different hyperparameters for each agent, a lot of different hyperparameters combinations, excuse me. So the first is the cumulative rewards flag. I already mentioned that the cumulative rewards was an optional input. It was not always given. So either true or false, depending on whether the cumulative rewards were fed or not to the agent every time step. Then there's the DQN model that was used. As I said, we used 4 different models, all following the same structure, but having a varying number of layers and nodes, so different complexity essentially. And these are the names that we will refer to them in the results that we'll show later. The specific implementation detail for this for these are in the paper. And finally, the utility function set used. So these are the 4 utility function sets I introduced before. So we just take the Cartesian product of this, and this means 2 times 4 times 4 different experiments. And for each experiment, we train 6 different agents, just so we can get an average value and a standard error. And then we evaluate them. So let's go on to the results. The results that are shown here are the results for the utility, the average utility. These have the problems that I was listing before, namely that we can't compare across utility function sets, but they are still useful because we can compare across a along a single utility function set. So for example, we can compare across models like this. So within agents that were trained with linear utilities, we can compare tiny, small, medium, and large, and obviously larger models outperform smaller ones. We can compare also linear agents with cumulative rewards linear agents, because cumulative rewards linear agents simply have another input, but they're being evaluated and fed the same utility functions coming from the same family. So this is also possible. What is not possible, however, in this table is to compare across different utility function sets. What we can see from this, as I previously mentioned, is that performance generally increases intuitively as the model size grows. However, this is not always the case. And indeed, for non-linear utility functions, we get an interesting phenomenon where we have, for the larger models, severe drops in performance. This is due to inconsistent training. Basically, sometimes the models get stuck in suboptimal policies, and it seems that larger models might be a bit more affected by this, are more affected by this. And when they get stuck, their performance drops severely. And in fact, you can notice also that the standard error gets higher usually. And this is because there are models that are performing well, but there are also some which didn't manage to get out of the suboptimal policy, and they are decreasing the average here. But what's also interesting is that the cumulative rewards are improving this. So in both cases, they are kind of stabilizing the training process and making it more consistent. In general, this phenomenon of inconsistency of the training process has been observed for all the models, even though, I mean, there are other results that are not shown here, but it's been seen even for linear agents. But for sure, for non-linear agents, the problem is more severe, and probably due to the larger complexity. So there's definitely work to be done when it comes to managing the training process. The other interesting thing is that, I mean, linear agents obviously outperform non-linear ones when we're only evaluating on linear utilities. This is should clearly be the case, because linear agents could specialize to those utilities. However, whilst we can see a steady increase as the model size increases for linear agents, we can see a steady increase in the utility function average, in the final utility average. For nonlinear agents, this does not happen. It seems that they kind of stall. They find probably some generally good policy, but even as they gain complexity, they don't actually manage to gain that much more performance when evaluating on linear utilities. The next batch of results has to do with non-dominated end of episode CRVs. So here we're just counting how many different non-dominated end of episode CRVs each agent manages to get. And we can see here that specifically dual threshold agents manage to outperform linear ones. They find more non-dominated, more unique non-dominated end of episode CRVs. Threshold, I mean, this is kind of expected, or to be expected, because dual threshold agents have access to something that linear ones and threshold ones do not, which is that dual threshold agents can take only some of an item, because they might be interested into up to 2 reds and then stop. So they might close an episode early, whilst the linear and the threshold agents, they either are interested in an item or they are not. And if they are interested in an item, then they want to take all of it. And if they are not, then they don't want to take any. And so dual threshold agents have access to this more different behavior, and this allows them probably to reach, and this is to be expected. This is coming from the known Pareto front limitation that we were talking about. Target utilities, one might notice, have very low numbers. This is not because they are underperforming. It's just because if you look at the specific definition of the sets and how the target, like by the nature of the target utility, there's just that many, but much fewer utilities that were evaluated upon. So just as a reference, each agent was evaluated on roughly 180,000 episodes on the fixed environment with 180,000 different utilities. But for the target utility, it's about 1,000 times less that. So it's more than understandable that they're underperforming, and this makes their results not really comparable when it comes to looking at number of unique policies and stuff like that. But we'll see how they'll still be interesting later for our results. In table 4, here we see the percentage of episodes where here I refer to it as a combined non-dominated event of episode CRV. So what are we talking about here? So non-dominated CRVs up until now were non-dominated at the agent level. So they were non-dominated amongst all vectors, all reward vectors that the agent itself managed to achieve. Combined non-dominated end of episode CRVs instead are non-dominated across all agents. They're the non-dominated by combining all the agents together. And here we're looking at how many times these agents manage to reach these, because okay, it's good that dual threshold agents manage to find a lot of non-dominated reward vectors, but how often are they using these? How often are they using the good ones? And what we can see here is that in general, they are outperforming linear agents. The results get a bit lower when it comes to larger models, and this is due to the training issue I was talking about earlier, but they are outperforming linear agents. So they are using more the combined non-dominated reward vectors than the linear agents. The next table shows instead how many times do we get the correct one? So an agent might get a very good non-dominated end of episode CRV, like one of the ones that is non-dominated across all agents. However, if it's the wrong one for this specific utility function in this episode, then it's meaningless. If it's the best reward vector for when the agent is interested in yellow items, but the utility function is actually asking the agent to take red items, then it's useless. I mean, the agent took a very good reward vector, but it did so inappropriately in the wrong occasion. So here we look at when they are choosing the best cumulative reward vector, non-dominated one, for the specific utility function we were using in that episode. And what we see here is actually that they have kind of lackluster performance. Linear agents outperform them. Threshold agents are kind of closer to a performance of linear ones, even though they are still beneath it. And it's probably due to the same distinction I was making before, where dual thresholds have a more different behavior than threshold ones to the linears. But yeah, like this is a problem that non-linear agents seem to have. They seem to reach non-dominated reward vectors often, but they do so inefficiently. The next table shows instead which of the overall of the combined non-dominated reward vectors each agent managed to find, what's the percentage of them. And we can see that in general, dual threshold and target agents outperform linear ones, specifically for smaller models. I'm not highlighting larger models, both because there's the training issue again, and also because the effect becomes a bit more inconsistent. But I mean, it's definitely surprising, especially for the target agents, that they managed to find so many, considering how little they're being sampled upon. Yeah, this is the table of these famous combined non-dominated reward vectors across all. I mean, here you can see them sorted, and all of this is in the paper as well. So what are the conclusions here? Well, nonlinear agents are definitely good for discovery and usage of CRVs. However, they do make quite a lot of mistakes in selecting the policy that they go for. And they also have a problematic training process, which needs to be addressed. Future work should probably focus thus on, first and foremost, new problem domains, because this is a toy problem and a very simple one. They should also focus on possibly expanding with new sets of utility functions. Polynomial utilities could be interesting, considering that the polynomial family has the property of being capable of arbitrarily approximating any function. So that might be interesting. Further, the training process issue needs to be addressed, and the training process needs to be stabilized. This could be done, for example, by improving the agent architecture or improving the training hyperparameters. If I were to make a recommendation, I would not continue as we've done in this work with having an agent output scalar Q values. I don't think that it's good for the agent to try and approximate the utility function. I think the agent should instead estimate the vectorial Q values, so the expected reward for every objective, and then the utility function should be applied. The exact utility function should be applied on the agent expectation to then determine the argmax of this and apply a greedy policy in the case of a DQN like we were dealing with. And this shouldn't be problematic as an assumption to use the utility function, because in general, the agent needs to have at least a utility function parameterization. So I can't really think of a scenario where one would have a utility function parameterization, but not access to the utility function itself. It would also be interesting to adding new evaluation procedures. These ones have the limitations I've highlighted here and that are highlighted in the paper, and new ones are definitely necessary for our scenarios. And yes, so this is the end.